All right, start the recording, share my screen. Admit whoever just showed up late. I know I was late, but class starts when I get here. Isn't there some sort of rule where what is it? If I have a master's degree, you get like 5 minutes. PhD, I think you get 10. Whatever. There's some breakdown. All right. So let's see. For today, we had this paper, right? To look at targeting compiler. Okay. Yep. So for today's class, we wrote, we researched why we need a compiler to know both the target architecture as well as the target operating system. So what did we find out? I think we talked about this a little bit yesterday or Monday, whatever. But tell me if you found out anything else interesting. Why does a compiler need to know both of those pieces of information?
So they have a direct, briefly, they have a direct relationship. From what I've read online, they have a direct relationship with the hardware, the target CPU architecture, and the operating system. Briefly because of the process of the compilation itself, because eventually it will work with the CPU in order to understand the machine. It needs to know the machine code that it will translate to. If I'm making the correct assessment here. Also, the operating system, because eventually the program which is going to execute, the compiler needs to know which operating system it's going to execute on. So, yeah, the program is going to work on. Am I correct?
Okay, well, so let me say what you said, and I'm going to ask you a follow-up. Okay, just so they can hear it online. So he basically said there's a relationship. Well, he basically said that you need to know what architecture you're targeting so that it can produce the right assembly code. That's part one, right? And then, oh, was that you? And then part two is you need to know the operating system because you said it's ultimately the operating system is going to run it.
Yes.
Right? Okay, tell me more about that part of it. What do you, specifically, why does it need to know what operating system we're targeting? What benefit does it have if it's targeting Linux versus Windows, for example?
As I said, from a high level perspective, I'm just saying that the executable program that the compiler will eventually output, if I get an exe executable Microsoft program, it won't run on my Mac, which is basically a Linux.
Okay, so maybe one reason is the output of compiling a program on Windows would be a .exe, whereas the output of compiling a program on Linux would be a different kind of executable file, some kind of binary, and potentially different on other systems. Okay, that's just the name of the file. So on Windows, anything DOS based, a file that is a .exe file that's said to have a MIME type of executable. So when you double click on it, it knows to try to run that through effectively the command line. .bat also will do the same type of thing. All right, so but what's the difference of what's in that file? Let's dig a little deeper. What would be in that exe file that would be different than what would be in that executable on Linux?
The assembly code might be different to call the function.
Okay, why would it be different? If both the Windows machine and the Linux machine are both running Core i5 processors, let's say. They're both running Intel Core i5 processors. Why would the assembly language inside of the exe versus the executable for Linux, why would it be different?
I mean, the set of instructions given by each OS might be different.
Okay, so let's replace set of instructions with system calls. All right, so an operating system has a collection of functions built into it, right? And things get accomplished in that operating system in terms of those functions that are built into it. Now, realistically speaking, if we just kind of operate from the perspective of a person who's writing an operating system, realistically, most operating systems accomplish the same kinds of things, right? They can write to the screen, they can read from the keyboard, things like that. But the function names for writing to the screen might be different on Windows, or take a different number or type of parameters on Windows than it does on Linux, so on and so forth. Okay, so ultimately, those functions are a little different. So that executable, the assembly code, since it's running on an operating system, it's going to need to utilize those functions differently. So what we're going to look at today is, to start off with, is Hello World in assembly for Linux. We did not look at that last class, right? So what we're going to do is we're going to see this in action. We're going to see the output of presumably a Hello World program written in C, let's say. Then we compile it, and it's going to turn it into assembly code. But specifically, it's turned it into assembly code for the i386 architecture, which is effectively Intel, running on the Linux operating system. And you're going to see here how it's actually using a power tool, even as a low-level language where we expect everything has a one-to-one relationship with the CPU. It's still leveraging that operating system to save the compiler from outputting a lot of code. All right, everybody can see the screen here online. It's shared. All right,
Yes.
so I won't go in too much with the structure of this, but effectively our variables are defined down here in the data section. So we have a variable called MSG that holds Hello World. We have another variable called LEN, which is the length of Hello World, the number of characters that are in it. Just roll with that. Okay. Now, up here, this is the real magic that we're going to look at first. So we're going to call that little chunk of code there the mechanism by which we make a function call to one of the operating system calls. Okay, so since we're dealing with Linux here, there is a system call in Linux called syswrite. All right, this guy exists in the Linux operating system. And syswrite requires 3 inputs. So this is a function, and that function requires 3 inputs. It wants to know, where are you writing something out? So are you writing it to the screen? Are you writing it to a file? Are you writing it to a printer? You know, where are you writing it? Okay. Then it wants to know what you are writing, and it wants to know how long it is. So it knows when to stop writing bytes that live in memory. Okay. So syswrite is a function that requires those 3 parameters. Now, the Linux operating system, so what we're doing here, these first 4 lines here are just moving values into little memory locations called hardware registers on the CPU. All right, so we're moving the thing we want to do, which is syswrite, which just happens to correspond to, magical system call number 4 on Linux. Okay, so somewhere in the Linux kernel documentation, it lists all the system calls, and system call number 4 happens to be syswrite. And system call number 4 is expecting to find inside of this specific register, EBX for Intel, is expecting to find the place that you're going to be writing out to. And again, inside the Linux kernel documentation, the standard output stream, which would be the monitor, happens to correspond to the value 1. That standard output stream is 1. Okay. Standard error is probably 2. That would be still going out to the monitor, but it's actually a separate stream. So you could separate those for log files, error files, things like that. But for us right now, just view it through this lens that in the Linux kernel, the number 1 when talking about output streams is associated with a standard output stream. Sure.
When the first question is when he says move EDX and location 1, EDX is that from 2 or am I getting it wrong?
What do you mean from 2?
Move is the function, EDX is from, 1 is 2.
No, this is the destination. So we are moving something into a destination. We are moving the number 1 into the storage bucket. All right, so we're putting in, so the Linux system call expects us specifically to put inside of EBX where we're writing it. It expects us to specifically put inside of ECX what we're writing, a pointer to where it actually lives in memory. And then it expects us to put into EDX the number of bytes that we're writing. All right, so these first 4 lines are all about just kind of setting the stage for a system call, okay? We're putting a value inside of EAX, a value inside of EBX, a value inside of ECX, a value inside of EDX, and then we're going to interrupt and we're going to call upon the Linux kernel. All right, so address 80 would be in kernel space where the Linux kernel lives. So we're saying, Linux kernel, you take over. I have set the stage for your first power move. All right, so the Linux kernel immediately then is going to go and look in EAX. And it's going to say, what is it that you've woken me up for? All right, and it's going to see, you want me to perform system call number 4. Good choice. Good choice. That happens to be syswrite. So it's going to say, I expect you to give me 3 parameters. Let's go look in EBX, CX, and DX, and we find, where do you want me to write it? What am I writing? Well, where is what I'm writing? And then how many bytes long is it? And then it will do all the heavy lifting. Somebody else wrote this syswrite program, right? And they compiled it. And the output of that is probably some scary assembly code that didn't need to get outputted by the compiler for us here, because we are leveraging that predefined executable already built into the OS. It's as a power tool, right? If we didn't have the Linux operating system in this case, instead of leveraging that power tool, the Linux OS right here, we would have to have all the assembly code in here that ultimately wrote something out to the screen. We would have to have it implemented in our program syswrite, which would be scary, okay? And that's scary on 2 sides of the coin. On one hand, we would have had to write in the high-level language, let's say, and this becomes a little bit of a catch-22, and we'll talk about that in a second, but we would have had to write in the high-level language all that extra magic to ultimately get something written to the screen, kind of almost speak at the machine level, speak to the computer directly, bypassing the operating system, which seems daunting. At the same time, the people who wrote the compiler would have had to write a much more difficult, well, would have had to solve a much more difficult problem, right? They are no longer writing a compiler that outputs for an OS. Now they're writing a compiler that outputs for an architecture only, right? Which is going to be pretty scary output. So right off the bat, when you just glance at this, you think, well, you know what? A hello world program in C or C++ or Python or whatever is pretty simple. You know, an older language like C, hello world is maybe a little bit more verbose than we want it to be, but it's still shorter than this. It's still less daunting than this. This looks like a lot of gibberish at a glance, right? Until you dive into it and really look at what it's doing. And now that we walk through it, it actually is doing a pretty simple thing, right? It just takes a lot of lines to accomplish a pretty simple thing. Load some crap into registers, let the OS take over, right? Special move number 2, what happens down here is, remember, Linux looks inside of EAX to find out what you're asking it to do. So now we're loading randomly the number 1 into EAX, which happens to relate to the system exit system call, which kills a program, makes the program stop running. And the system exit system call can optionally return a value, all right? So it can, typically in Linux, you would have, when a program exits, maybe it returns a 0 saying everything went fine. If something bad happened, it had had trouble writing out to the screen or had a corruption in some way or something like that. Maybe you have an error code of 17, and 17 means the world is ending or something like that. Whatever it is, you can have as many error codes as you want, up to, I'm guessing that thing is size of int. So probably 2.1 billion error codes if you really wanted to take advantage of it. It's possible it's actually implemented as a byte or a short. So, you know, minimum you can have 200 or probably 127 unique, 128 unique error codes. Well, I guess you could have a negative number for an error code. So you could have 256 error codes in a worst case. Probably not going to take advantage of that, right? You know, your simple little hello world program comes with a book listing all the 256 possible things that could go wrong. Probably not going to do that. Okay, but anyways, the sysexit system call, which is provided by Linux, expects a single parameter. And I'm telling you, it's actually an optional parameter. You don't have to give it to it, and the default output would be 0. But they've given it to it here in this example. So again, we load EAX with what we want to do. That's where Linux expects you to put it. And then we load EBX with the one parameter, because sysexit only takes in one parameter. Notice that ECX and EDX still have the old stuff in it, right? ECX still has message loaded in there. EDX still has length loaded in there. It just so happens that system call sysexit doesn't look in there. It doesn't need them. So, you know, we could have decided, hey, we're going to clean up those registers if we wanted to, but we're just going to set them back to some default value, 0 or something like that, because they're just going to get overwritten by the next program. So that's why we're not cleaning them up or anything. We just happen to not be using them down here. So we're saying, I want to do sysexit, and here's my return value. That's going to be the parameter to sysexit. All right. And then just like before, we'll interrupt. We'll tell the Linux kernel, take over from here. Linux kernel will come in. It'll look inside of EAX just like it did up here. Okay. We're kind of seeing that cadence that the OS does, right? You know, OS swoops in, it looks in EAX, EAX tells it what to do, then it goes and grabs the parts, the things that it needs that you've hopefully provided it to do what it needs to do. And then it magically does it. And as you might guess, sysexit probably results in this program terminating, right? Whereas syswrite probably resulted in this program writing something somewhere to the screen in this case. Okay, makes some sense what the how the output of this thing kind of look like? All right, so now that we've walked through it and explained it, pretty simple to understand now, right? But at a glance, it's intimidating, right? You know, assembly is an intimidating thing. We're going to be looking at ARM-based assembly in here, which is the assembly code that typically is used for on modern mobile devices. Pretty much all of our, if you have an Android or an iPhone, you're running some sort of ARM architecture today. So we'll talk about that some more as we get to it. But this is Ia386 presumably architecture, which is I mean, every single time a new Intel processor comes out, it adds some new magic tricks, new things that it can do at the CPU level, which may or, and then every single time a new OS comes out, it might update an old system call or add some new system calls or whatever. And if it updates one but keeps the parameters the same and just accomplishes it in a more efficient way or whatever, well, then the assembly doesn't need to change, right? You're still calling the same magic trick. You're still passing it the same parameters. It just is presumably performing it in a more efficient or secure or whatever way. So in that case, when you get the new OS, maybe your old programs still work. In fact, that's typically the case, right? You know, but you at some point, sometimes OS, we get a brand new OS or a major update or an architecture change, things like that. Old programs might stop working. And in Windows, you've probably seen before, you can run a program like in compatibility mode, right? And what does that try to do? It takes the assembly and it tries to map it to the new way of doing things, right? And you may or may not have good success with that because it's saying, look, this old program, when it does a syswrite, for example, I'm just making this up, but if it does a syswrite, because of when that was written, it's only passing it 3 parameters. But the new fangled version of syswrite takes 11 parameters. So I'm going to go ahead and fake those, those other parameters for it, pass default values in or whatever. So hopefully this program will function. at some level, right? Okay. So questions about what we're looking at here. So hopefully this kind of demystified something that looks pretty intimidating.
Yes.
So I encourage all of you sometime this week to walk into Best Buy, go and find somebody from Geek Squad in Best Buy, print this out and go up and explain it to them. Videotape the whole thing and post it on YouTube and tag me. All right. So that's kind of the output, the punchline from our homework assignment. So I had you look into it, then hopefully I've just filled in some of these gaps that we had. Okay. So we talked about this. I'm going to ask a question here.
I want to ask a question first.
Sure.
In the previous slide, the other slide, which the title says, what a compiler requires. From what I read, that modern compilers or any compiler now can adapt to the different operating systems and architectures. With the, I haven't read in depth, but I've read that something called porting in compiling mode, which makes it efficiently adapt. So what I mean is it doesn't require an operating system or an architecture. There is a relationship, but I think it does not require.
Well, but no, it still does. So you're saying, okay, like a modern compiler, like GCC, one of the, GNU compiler collection is what GCC stands for. And GCC knows how to target, I don't know the full list, but a multitude of architectures and a multitude of operating systems. Even historical ones that might not be very common anymore, but hey, it was there before. We can target MIPS running some old Unix operating system or something like that. When you compile, it still is, the compiler still needs to ultimately know the architecture you're targeting and the OS you're targeting, because it's going to produce a executable specifically. I mean, that's kind of what you said earlier, right? It needs to produce an executable that could run on that guy. Now, modern compilers, they have the flexibility to potentially target different architectures and potentially target different compilers, but you would still need to compile more than one time for each of those architectures. So I think what you're really saying is it's a confusion between the person writing the compiler and the person using the compiler. Right. Us, we're the users of the compiler, and we just happen to have a pretty, time-tested, evolved tool like GCC, for example, that already knows about a bunch of architectures and a bunch of operating systems. So presumably, we can write a program once, and as long as there isn't some very OS-specific stuff in our program, we could compile that same program, like more than likely Hello World, for example. Doesn't have a whole lot of earth-shattering functionality, right? So chances are we could take that same standard C program and we could compile it 3 or 4 different times, targeting different OSs and architectures, and get 3 or 4 different output files that would be executable on those particular OSs and architectures with a single tool. That compiler, because the GNU compiler collection has been around for a few minutes, and through those years, it's gone through all those different architectures. They just keep adding crap to it, right? That's why it's called the compiler collection. Okay, it knows how to do all that stuff. All right. So what if we don't have a target OS? So when we think about our computer, let's draw a picture. I like drawing pictures. It shows my keynote prowess. Let's do that. Shapes. All right, so we have our computer. And, oh, that's fine. we have our architecture that lives on that. It's actually probably the other way around. Let's go this route. So when we say architecture, we're really talking about the CPU, right? Okay, so the computer has a CPU. Now, we typically expect there to be an operating system that sits there. And then we have our compiler. And we'll make the compiler blue. All right, now this compiler typically would need to know, this is what we just finished talking about the operating system and about the architecture. Those pieces of information for it to produce an executable Okay, so that's effectively what we just explained. Now, what if we took away that connection? What if we did not have a target OS? We only had a target architecture. Are there any programs we might write that wouldn't actually target an operating system? And I say that loosely because I'm kind of hiding the punchline here a little bit. Yeah, so let me ask you this way. Something like Hello World, very simple program, just displaying something on the screen, right? When you first turn your computer on, does sometimes things appear on the screen before your operating system loads? Sometimes it'll show like a memory count, or it'll be like a little Apple logo type thing, whatever. There's stuff occurs on your computer visually a lot of the time prior to Windows launching or Linux launching or Mac OS launching, whatever it is. All right, so what is actually running that program?
Not program, the things prior to the operating system is the architecture. Well, I think
that's this piece.
I was gonna say it that way. The program that is not intended to the end user might be running through the architecture.
We have our computer monitor here. We'll just use this as our syswrite example. So here, I'm going to specifically put Linux here since that's the example we've been using, right? Linux knows how to talk to the monitor through syswrite. All right. But you just finished telling me that when you first turn your computer on, sometimes things appear on the monitor prior to Linux loading. So the computer knows how to talk to the monitor as well. By what means, what mechanism does the computer know how to talk to the monitor? Remember, the architecture, the CPU is just a workhorse, right? I feed it stuff and I feed it instructions and it does those instructions. All right, so he doesn't know how to talk to the monitor innately. He can just move stuff around in memory and stuff like that. So how does the computer talk to a monitor without going through the operating system, without going through Linux in our example here.
I'm guessing some kind of embedded language.
Embedded language. Well, I think we're getting close to something. Yeah, I'm going to put something in here. I'm going to replace the word computer with motherboard. Okay. And I've run out of colors. Wait a minute. Look at that. New color. What goes right here? What sits between the motherboard and the Linux operating system? The kernel would be part of Linux. Linux is a distribution, so really when I say Linux up there, I'm talking about the Linux kernel. So here this is the Linux kernel we're talking about up here. Who launches the Linux kernel? Does it just magically happen? You turn your computer on and poof, an OS starts launching?
The BIOS?
The BIOS. So this is the basic IO system, right? This is effectively, a little bit ago we talked about that one of the things that an operating system typically does, kind of all operating systems accomplish that same base tasks, base collection of tasks. Are one of those tasks the ability to read stuff in and write stuff out? Standard IO, input output, that's kind of something that every single operating system should know how to do, right? Okay, so with that in mind, this very simple operating system that actually lives on a little chip on the motherboard, it knows how to write stuff to the monitor. You know that's true because you've seen it. You've seen stuff on your screen before the operating system actually loads, your traditional operating system actually loads. All right, so if I am not targeting a specific OS, that means that the architecture is going to specify the BIOS type that we're using. All right. Now BIOSes don't update very often, or they get bug fixes, stuff like that. But we are moving to some newer technology in BIOSes now, so they've had to redo some OSs. Sometimes you'll see that, like Mac OS. One of the reasons the Mac OS won't install on a Windows hardware-based machine, it only installs on Macintosh hardware without some workarounds, is it expects a what's called an Efi based BIOS. So it's a kind of a different operating system, right? It's a different operating system, and the Mac OS knows how to interact with that kind of BIOS, whereas Windows knows how to interact with a different kind of BIOS. Part of that is on purpose, right? Apple might say, well, an EFI BIOS is better, more modern, something like that, but which may or may not be true. You can probably make some arguments all sorts of different ways. It does seem to be trending in that direction, that everybody's switching over to EFI. But regardless of that, it would certainly be in Apple's best interest for you to have to go out and buy an expensive Mac if you want to run their free operating system, right? So that's kind of the idea there. But if we didn't have a target OS for our compiler, what we'd actually be doing is your code would be targeting the BIOS, okay? And you've probably heard of some of these things before. We have something called like a bootstrap program, where that's the guy that does the handoff. So the bootstrap program might run on the BIOS. So it's kind of a precursor to the in our case here, the Linux kernel. And his whole job, he's this little tiny program that's probably way more complex than it should be because of the level in which it has to operate. And its whole job is to go from a computer that basically does nothing to handing the ball off to a, powerful OS like Linux, and getting it launched into memory so that we can actually do some real stuff. Okay, somewhere we have to do that transition between the BIOS and the core operating system, or our big boy operating system. Okay, that makes some sense? All right, so we do have, now there are some tools available for OS rating that allows us to target we're still targeting an OS, just the OS we're targeting is the BIOS, right? A much simpler OS, so we've removed a lot of those magic tricks, so you would assume that the assembly code output of that would all have to be outputted in terms of the BIOS. It couldn't make assumptions of any system calls that are available in the higher order operating system. All right, does that make sense? So a compiler could target the BIOS, or it could target the kernel. So it always targets an architecture. It always targets an operating system. The complexity or power of that operating system is what's in question. It could be a very simple operating system where a computer needs some starting point to bring all of its pieces together, because a computer is just a bunch of stuff soldered together otherwise. You have your memory of all these things we've been talking about, but unless you have some basic piece of software that makes them all talk to each other, even if it's relatively uninteresting what you could accomplish with it, you're kind of dead in the water. It's like a car without gas in it. Can't turn it on, or a Tesla without a battery charge. Okay, a lot of really interesting stuff, but none of it works. All right. So let's keep trucking here. All right, so we've already talked about some of this. So when we talk about computer architecture now, we're kind of thinking about the people who make the processors, like Intel. So they're talking about the system design of that. So what's the actual chip look like? And how is it put together? How many magic tricks does it have? That kind of stuff. So, computer architecture is an outline of the major components for a computer system. It's comprised of memory, storage, processing capabilities. So we've talked about all of that, but that also exists within the CPU itself. How many hardware registers are there? How many, what are the different sizes of those hardware registers? We were just looking at EAX, EBX, CX, and DX, and those guys, EAX is a 32-bit register, where AX is a 16-bit register. AL is an 8-bit register, so on and so forth. Okay, so we have, more modern processors even have 64-bit registers, or modern CPUs have 64-bit registers. Some CPUs even have 128-bit registers, but that's probably not overly useful yet. So you have how big the registers are. You probably are going to have several different sizes, most commonly 8, 16, and 32 with some 64s mixed in there. And then how many of each of those? These are decisions made by the various architectures, because you are limited no matter how many special magic tricks a CPU knows how to do, regardless of the kind of CPU. It is still reliant on the your way to interface with those magic tricks is reliant on being able to store stuff inside the processor, store bits of information and stuff like that. And if you aren't able to put all that into the processor and you still need to accomplish something, you'll have to offload some of those things into L1, L2 cache, maybe system memory, maybe even hard drive in a horrific situation. And that comes at the cost of performance, right? The stuff, if you can get stuff loaded directly into the CPU's hardware registers, then you're going as fast as you can go. The second you have to start taking steps further away from the CPU in terms of where you store your pieces of information, then you're going to have, you know, a commute time if we think about our computers in terms of like a interstate system driving. Okay. So then we have our instruction set architecture, ISA. This category focuses on the particulars of the system's main processor, things like word size, addressing modes, registers, things like that. But not just that. When I think of instruction set, I also think about, you've heard me mention them, I call them magic tricks, things that the CPU knows how to do. And there's going to be a list of those. And one of the things we're going to talk about in here, specifically with the ARM architecture, is the ARM architecture follows kind of a, think of it as a mindset of something called a RISC processor, a reduced instruction set processor. So rather than saying, hey, you know, if you're Intel and you're designing a CPU, so typically Intel CPUs are made for, you know, powerful computers, right? So maybe it's a desktop that plugs into the wall, or a laptop. And now they have made some low power Intel ones for like more portable laptops and stuff. But to really drive this point home, let's think about Intel when they make their desktop class processors, which are their most powerful processors, right? How many of you have built a computer before, or done some sort of you know, adding memory to a computer, been inside of a computer doing something? Is it a fair assumption that all of you have either done that yourself or seen somebody do that, or kind of have an idea what you might be looking at? When you open up a computer, have any of you ever seen a computer with some gigantic fan in there that's sitting on top of the processor? Usually you have a big heat sink and then a fan that sits on top of that. Some of the more modern computers even have, like gaming machines, have liquid cooling. Okay, so when Intel made that processor, all they were thinking about is speed, right? And you know, they had to think about heat a little bit in that they didn't want the processor itself to melt. Okay, but the idea is that if you want all that power, what you need to bring to the table is some beefy mechanism for keeping it relatively cool. All right, so it doesn't melt or catch fire or something like that. All right, so we might say that Intel's focus is on, at least at the desktop level, is on pure compute power, paying not that much attention to conserving power in terms of electricity, things like that. Not that they completely ignore that, but it's down their priority list, right? You know, they're thinking about number of cores, speed of cores. How can we add a magic trick that says this next processor is up to 50% faster? I like that from a marketing perspective. When you get this year's Core i7 processor, which is what, Series 10? I think it's Series 10 processor, versus last year's, the 9000 series. You might see in like the advertisements that it's, you know, up to 60% faster, something like that. Well, you know, just like we kind of know when you see commercials for different things, they typically tell us in commercials kind of what we want to hear, you know, something that convinces us. So when they say something is up to 60% faster, that means that there is some circumstance in which this processor could be 60% faster than the previous processor. Maybe they've added a new magic trick. Maybe they've updated one magic trick. So if the moons align and you're doing something very, very, very specific on that CPU, you potentially could see a speed increase of 60%. Now, under most circumstances, though, you're probably going to see very little of any speed increase. Okay, so what I'm effectively saying there is if you built your computer last year and you have the, you know, last year's Core i7 processor, you don't need to feel like you need to run out and get this year's Core i7 processor. You know, look at the tech specs on it and see whatever they've added, does it benefit however you use your computer, right? maybe they added some feature for, I don't know what the feature differences are between the latest i7 and the previous i7, but let's just make something up and say maybe they added a feature to make video rendering up to 60% faster because of they added a magic trick or something. And so if you're in the world of video rendering, you're creating animations, things like that, you might say, hey, this is worth the investment because this is going to decrease the time it takes my computer to do that specific task that I do all the time. Then it might be worth it. All right. But if the new feature allows you to, I don't know, work with Excel documents more efficiently, and you say, well, I never use Excel. It's not something that's part I don't need a spreadsheet, or I rarely use a spreadsheet. Well, then getting that new processor, which just beefs up your productivity in Excel, isn't going to benefit you at all. It's only going to hurt your pocketbook, right? Okay, so that's your instruction set. This is the collection of magic tricks that the CPU has. Now, when we talk about microarchitecture, this focuses on the organization of the system's main processor, like data paths and storage. So this kind of, we talked a little bit so far at the high level of these hardware registers that live on the CPU, and we're going to get into specifically those things in ARM-based processors maybe next class. I did also mention at some point today, L1, L2 cache. So, whether you know what those are or not, you've probably heard those phrases before. If you're looking at, a processor online, you're looking at some server processor, it might have a lot bigger chunk of L1 or L2 or L3 cache than the consumer-based processor with the same name at, significantly more of the cost, significantly more cost. Well, the idea is that cache is still faster than system memory. So the idea here is that you have your hardware registers, which are going to be super fast memory. Then you have L1 cache, which lives on each processor, which is very fast memory. Then you have L2 cache, which also lives on each individual processor, which we can say is almost as fast as L1 cache. Then you have L3 cache, which actually is shared between multiple cores on a processor. So this adds a capability as well, but also gives up a little bit of speed, so on and so forth. The farther you get away from the CPU, you finally get to your hard drive. That's where you're dealing with your slowest storage medium, your slowest memory. All right. All right, so we've kind of talked about this already, difference between PCs, workstations, mobile devices. PCs don't care about the amount of electricity you're taking, mobile devices maybe do. Workstations are, even less about the electricity, and also going to, maybe make the assumption that the machine's going to be used more for like a professional level thing. Or if we also throw the idea of a server in there under the workstation category, where you might have multiple users using this computer at once. So you figure if you have an email server or something like that, any kind of server-based computer, that doesn't really dictate what that computer might have in it, but it does tell you what maybe that computer should have in it. Because if you have a server that might have 10 users simultaneously on the computer, that doesn't mean that a single human being who's a pro-level user won't put the computer under its paces as much as 10 minimal workers do. But I think a reasonable assumption would be the more people who are simultaneously using a computer, the more resources that computer needs in order to kind of keep up. Because ultimately the job of a computer is to trick the end user out to make us feel like we're getting all the love from the computer, right? Okay, it's doing our bidding, and it's doing it as fast as we want it, no matter who else is using the machine. But certainly, our focus in here goes towards this mobile devices thing. We have to really change our mentality of, because as human beings, we still want it ultra fast. Right? We want more memory, we want more speed, we want more cores, we want more pixels, we want more, including more battery life. We want bigger screens, but we also want it to fit in our pocket. So it has to, you know, we don't want the phone to be arbitrarily large relative to the screen. So, you know, one of the things people talk about, well, how big are the bezels, right? When you get your new phone, you know, if you have a lot of, you know, dead space around the screen, you're like, well, that's just wasted space, and now it won't fit in my pocket. Something like that. You know, I have this the Note 10 Ultra, and you know, it makes it even worse. It has like no bezel. In fact, the screen actually curves at the edge. Like, look, we couldn't actually fit it. We couldn't fit it all on the flat surface, so we just wrapped the screen around. So, you know, that's real practical. So you can look at the side of the thing, or sometimes you end up hitting parts of the screen with your fingertips. Yeah, it makes no sense, this wraparound screen thing, okay? But it's also, they can say it's got the infinite bezel, right? You know, yeah, I think infinitely small bezel, whatever it is. All right, but punchline for us is we certainly could, we certainly recognize that decisions related to mobile devices are in a whole different world than the decisions we might choose for things that are tethered to a wall, right? Or workstation servers where you have lots of users using them at once. When we think about our smartphones or our tablets, iPads, things like that, you know, truly mobile devices like that, you know, we're typically not considering multi-users. We're considering making one user really, really happy. All right, so they can make design decisions related to that. Big screen, bright screen, everything feels like it's peppy, good battery life, yada, 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 yada. Okay. So we've already kind of talked about these things. So I'll skip some of these slides. You know, in fact, we just talked about this just in the last 2 minutes. So we'll just jump past this. Okay, we talked about that. All right, so let's talk about these hardware registers at a little bit more detailed level. Specifically, what's a register? When we're talking about hardware registers, so these guys, first of all, where do they live? They live directly on the processor. Okay, so when you look, if you open up that computer, I asked you earlier, when you open up a computer, when you open up a computer, I asked you, you know, do you see that giant, the giant heat sink and the giant fan? Well, you know, you could detach that. Once you detach that, what do you see underneath the heat sink and the fan? See, yeah, you see a little square thing, right? Okay, well, is that the actual processor? Okay, well, maybe it's kind of a loaded question. What's inside of that? If you have a quad core processor, do you see 4 of those, or you just see 1 of those? 1 of those. So inside of that single square thing, there's 4 somethings, right? Okay, and those 4 somethings are connected together inside of that square thing. Okay, so yeah, we can generically call that the processor, but it still goes deeper, right? There's more stuff in there. You know, embedded wires and small scale integration stuff to make all those things talk to each other, and there's memory stuffed in there, and there's all sorts of stuff stuffed in there. Now, if you were to pull that processor out and flip it over, what would you see?
Spikes.
You'd see what?
Spikes.
Spikes. Potentially spikes. On a newer processor, you actually see little dots. They're just metallic contacts. They don't actually use the spikes anymore. So if I do CPU, we go to images, I'm sure we'll get one. Yeah, so here's like a modern CPU. Can we get it up here? Ninja.
They're all gold plated only.
Yep. So see how these just have like little contact points on this one? Now I'll give you a second to count each of those. Okay, there's a bunch of them, right? Okay, if we go back in time, let me just do let's do a X86 CPU. Actually, here's an X86 CPU. Let me get you one that looks more like, let's do a 286. That'll, because technically this is a CPU, but maybe it doesn't feel like it is to us because it's not square. Okay. But certainly, it's not as ridiculous of a request for me to say, count the number of spikes on this guy, right? You could count those. It's got the same number on the other side. Okay, each of those little spikes is an I/O channel for that CPU. So it seems reasonable for us to say that based on just at a glance, it's kind of like you're in a meeting and you take a vote and you say yay or nay, and the yays scream and yell, and the nays, nobody says anything, or like 4 people say something, you kind of know who won. All right. So a modern processor, lots and lots and lots of little dots. Old processors, a lot less little dots, right? If we look at the 286 CPU, yeah, here's the 280. I want to see the bottom of it. Show me the bottom of it. Fine. That's 486. That definitely has the pins. .46. There we go. There we go. So there's the little spikes you were talking about. So there's the 486. Now again, these wouldn't be as friendly to count, but still less, right? Still less. So one of the things we might say that as our, that's from 1989. Actually 1989, that would not actually be a 486. That would be probably a 380. I don't think that's true. Well, it says 486 here, but I don't think this is a 486 chip. Unless this center thing is something that was produced earlier. 486 was not out in 1989. 486 came out in 1995, maybe. Well, now I'm curious. .486 CPU release date. Oh, you know what? The 486 DX2 processor was 1995 or 6. 1994 maybe. So maybe the initial DX or 486, maybe 486 XX processor came out earlier. Yeah, 1989. Yeah, see there's multiple. We have the DX, the SX, SL, GX, different release dates. Yeah, here's our 1992 was the DX2, 94 was the DX4. Okay. So the initial architecture was 89, but the notice this is the speed of it in megahertz. So the first one was a 20 megahertz processor. I had a computer with this chip. Well, actually, I had computers with older chips in it, but my first, what I would have called powerful computer that was a 486 DX2 66 megahertz processor. Now, what's interesting here, though, is this listed as March 1992 is when it came out. I want to say, did I get that computer then? Maybe I did. I would have been a freshman in high school in 92. Maybe I did get it my freshman year. I just distinctly remember we had to wait for the processor to come out. It was like the newest, latest, cool, like kind of like PlayStation 5, right? You were waiting for the processor to release. And guess where I bought my computer in 1992?
Where?
Where? What store they still exist today, or mostly exist today. I think they're still in business. Sears. I bought my computer from Sears Roebuck. Well, I didn't buy it. My dad bought it. but we acquired the computer from Sears. The Sears closed down here, but I think they're still in business, the company, but maybe not. They might have gone under. All right, but in any case, there's a little history flashback for you. All right, but in any case, when we think about a CPU, we have all those I/O ports. We've been talking a lot about I/O today, right? The spikes, the pins, these are the way that the motherboard. So if I go back here and I look at, let's do a 486 motherboard. That'll give us I want one without the chip in it. Well, here's an example of, so here's a 486 motherboard. You see, you got the little things that you drop the chip in there, okay? And this is actually after they had made them a little bit friendlier. This was what's called a Zif socket, ZIF. Might have been 2F. No, ZIF. Anybody know what a ZIF socket was? You see they had this little bar up here? So if you lift that bar, it releases the processor. So inside those little holes are little grippies. Okay, it kind of gets tight to kind of create a good snug contact with the those pins. So when you lift this up, it releases it. So Zif stood for zero insertion force. Okay, because before this, you had to kind of line up the pins perfectly and then apply pressure to push it down into the sockets, which that part wasn't maybe the end of the world, but what if you had to get it out? You kind of had to pry it out, and those pins would bend. I've had to bend pins back more than one time, and then when you break a pin off and you think, oh, that's not a big deal, it's a big deal. That pin's used for something. It's one of the I/O channels for that processor. All right, so anybody know the name of these slots? Back then? Oh, yeah. Well, they're different slots today. These are called ISA slots. Then once you got to newer computers, you had PCI. Now you have PCI Express. You have two different types of PCI Express ports today. All right, but in any case, here, this is you can see, this is where your RAM went. Yeah, these are PCI ports. These are PCI, not Express, just normal PCI. This isn't a Visa bus, is it? Well, whatever, it's in there. So you see that this has those little pin inserts. So when we marry that CPU to this motherboard, those pins go in there. We have to, you see how this part of it here has a little angle that allows you to line up the processor so you're inserting it in the correct direction. And here's that little bar thing again for the zero insertion force. But effectively, when you marry that CPU to the motherboard, you're dropping it in, making that connection to all those little I/O pins. So that this motherboard that has, see all this gold stuff? Those are wires. You can think of them like wires, right? So this is a printed circuit board. So these are all the ways that this guy communicates with all these other little chips and stuff like that on here. And the BIOS is going to live in probably this is probably the BIOS chip. There it is, AMI BIOS. So this is the kind of this is what happens before Linux. Um, but it's hard coded into the machine. So this motherboard has a BIOS that follows some standards so that the modern operating systems can talk to it and that kind of stuff. Okay, so we're all on a good page where we're sitting in the world here. Okay, now if you go inside of a mobile device, so if I were to crack open my smartphone, would I see something that looks kind of like this? Probably at a pretty vague level. Like you would see the equivalent of a motherboard, but it would, first of all, it'd be significantly more miniaturized, right? All right, so all the same crap would be there-ish. It would just be significantly miniaturized. A lot of these ports we're seeing here, these are expansion ports for adding cards and stuff like that. We don't have those, you know. And you don't got room for them, so you might as well not take up space for them. Right, so you know those would be gone, so we've saved some space there. We can't really add additional RAM to our smartphones. Some smartphones have like an SD card slot, so you can add some additional, like, think of that like hard drive storage, right? You know, but in general, the actual memory that's on it, that's in there, pre-installed. Okay, so you know, think about, you know, here, these are your memory slots for SODIMM memory, old style memory. Actually, this supports both. These are SODIMM. I think these are 30 pin memory, but whatever, doesn't really matter. I started building computers before this though. Wait, hold on. No, these are PCI ports. These are PCI ports. This is SODIMM memory. Yeah, no 30 pin on this. So in any case, you know, if you were to open up your smartphone, you would see a different kind of level of stuff, but all the same things would be in there. You'd have system memory. You'd have a processor somewhere. A lot of these things might not be so easily identifiable because everything kind of, they're called systems on a chip, right? So all this stuff that we're looking at here would be on a little tiny chip that's inside of your smartphone. If you crack open your smartphone, what will most of what's inside of here be? Yeah, so I'm hefting my phone here, and it has some weight to it. What weighs so much? The battery. Yeah, so if I crack this dude open, I'm gonna find it to be, I'm just gonna make up a number, but let's call it 107% battery. All right, it's a very high percentage of what is inside of that device is a battery. So they tried to make the actual system, the system on a chip, as tiny as possible to have more room for batteries. Apple, we think about Apple architecture. Those of you who have a MacBook, and a lot of other devices are going in this direction as well. You used to have people who are travelers. They had a replaceable battery in their laptops, right? You know, where you could have two charged batteries, and you know, then you can swap out, you know, if you ran out of charge or whatever, you can just swap out a new battery, have a full charge, and charge the other one later. Well, now your laptop, if you have a Mac, and really most other laptops as well today, but let's just use Apple as an example because they were kind of the pioneers for this. There's no replaceable battery, no replaceable battery pack. Why not? Why do you think they did away with that? Just to charge you more money? Well, probably, but but is there also a good reason to get rid of a replaceable battery pack where you like push a button and it releases the battery?
Other than they increasing maximizing the battery performance?
What do you mean by maximize the battery performance?
Increasing the
battery life?
battery, well, not life, I mean power.
What is required inside of the computer in order to support a replaceable battery? Yeah, to allow for that to exist. Probably some mechanical hinges and stuff like that. Stuff. right? We need stuff that allows it to accept a battery and, lock it in and then, push a button, it releases it and stuff like that. And guess what stuff does? Stuff takes up space. And what could you be using that space for? More battery, right? All right, so the idea is that, sure, they want to charge you more money. As soon as the battery starts getting weak, they either want to come in and charge you an arm and a leg to replace it, or have you buy a new Mac, right? But the reality is you did gain battery life, because what they did is said, look, no longer do we have a replaceable battery. So what we're going to do is we're going to take out all those little hinges and things like that we used to have in there to physically support a replaceable battery. And what are we going to do instead? Put more battery. Let's put more battery in there. So you crack open on a MacBook Pro here, you crack this thing open, it's going to be, I don't know, I'll make up another number. Let's call it 140% battery. It's going to be a lot of battery. All right. I guess realistically, it's probably going to be 90, certainly 90% or more battery that's inside there. The actual system itself is very tiny. So this whole idea of this motherboard with all this stuff has become so miniaturized now. With our ARM processors, and so, we no longer have replaceable RAM. Same thing in your, you have a Mac. Some computers still have the replaceable memory. You can add some more memory to it, but a lot of them have moved away from it. Apple moved away from it a while ago, where it says, look, give us as much money as you're willing to give us day one, because that's all the memory you're ever going to have in this computer, right? You can't go in and these are little RAM slots here. You can't go in, and when you first get this computer, maybe only one of these slots is taken up. Maybe there was a back in this time, maybe there was a 4 megabyte chip in one of these slots, and then you want to upgrade to 8 megabytes for your computer. So you have a whole free slot here. You just get another 4 megabyte chip. But if you want to go to 16 megabytes, you have to pull out the 2 4s, put in 2 8s, and and that kind of stuff. You can no longer do that, right? But what did you gain? If you no longer have to allow the user to put memory in and things like that, you no longer need this hardware here to have a receptacle for receiving a memory chip and these little clips for locking it in and all that stuff. You don't need that stuff in a mobile device, because you're saying, look, we're not going to let you do it. So we'll just hard code that memory right on into this computer on a chip. Trust me, it's there. It's in there. We've miniaturized everything, and you can't touch it. Okay, you can't do anything to it. It's there. Everything that you ever want, you better buy day one. Okay, so we can say, oh, well, that's expensive, blah blah blah, but it also leads to a very compact design. All right. So, homework. Write a 2-page paper discussing the high-level architecture of ARM-based processors. Specifically, what registers are available and how large are they? So talk about it in general, but we really want to get that introductory idea of what are the hardware registers inside of an ARM processor. They're not called EAX and EBX and ECX like we looked at today. They're called something else. How many are there? If you want, maybe pick a recent ARM processor from Apple or Snapdragon chips on Android devices for your example. And then maybe between those two, we'll have, some of the class will do. If you're an iPhone user, why don't you look at iPhone chips? If you're an Android user, why don't you look at a Snapdragon chip? I assume we probably have half of the classes each-ish in here. We're certainly going to have at least one of each in the class. So why don't you do that? If you're an iPhone user, why don't you look at one of Apple's ARM chips? If you're a Android user, why don't you look at one of the Snapdragon chips? They're both ARM based, so you're not doing yourself a disservice either way. Maybe that'll allow us to think about the differences a little bit. Cool. Questions, comments, concerns, bribes? All right, I'm heading down to chapel. Front row is always available. Feel free to join me, and I will see everybody on Monday. We do have a couple of new students in class. You hopefully have access to Blackboard now. You're gonna have to play catch up, so all the video lectures are uploaded on there. So go make sure you go and look at those and watch them and do the homework that was due this past week. So I'll give you, this week to catch up without counting stuff late, but do that as soon as possible. Cool. All right. Have a good one.